Earlier we talked about gradually varied flow, so this is depth and velocity changed over a long distance. Now we're going to talk about rapidly varied flow, which is depth and velocity change over a shorter distance. With rapidly varied flow, we need to talk about specific energy. This is the sum of the depth of flow and the velocity head. In equation form, that's going to look like E specific energy is equal to depth of flow plus velocity head, which is V squared over 2G. This is also called energy head. It's also called specific head. There is continuity with specific energy. So the energy at location 1 needs to equal the energy at location 2. Also recall that velocity is equal to the flow rate divided by area for incompressible fluids, which in general is what we're dealing with. So putting these two things together, we can have depth 1 plus flow rate 1 squared over 2G area 1 squared is equal to depth 2 plus flow rate squared divided by 2GA2. And I had flow rate 1, but with conservation of mass, these two flow rates should be the same. The areas are based on depth of flow. So if we have a shallow depth, and a small area, that means that we are going to have more kinetic energy driving our system. A deeper depth is going to be a potential energy flow. So here we've got two almost identical sluice gates here with flow, and you can see the energy grade line here is about the same height on both of them. One can see that the flow is conserved in both cases. At some point, there is a constant flow depth, and this is called critical flow. And this is where specific energy is at a minimum. With critical flow, we have critical depth, and we can solve for critical depth by taking the derivative of the specific energy and the depth of the water and setting it equal to 0. Recall that hydraulic depth is the area of the cross-section over the width of the channel and we can get critical hydraulic depth which is dc, and that is equal to the flow rate squared all over gravity times the area of the area where we have critical depth, and that is also equal to V squared over G. We can rearrange this to our critical area cubed over the channel width, the flow rate squared over G. So that gets everything into flow and area and takes care of that velocity, which is equal to flow divided by area. Remember that Froude number controls open channels. So when the Froude number is equal to 1, This is critical flow. Our summary of critical flow, all the main points are: 1, E is at a minimum, so that's the specific energy, and that's when flow rate is at a maximum. It occurs when we reach that critical equation of area over the channel width is equal to flow over gravity. And it occurs when the Froude number is equal to 1. By the way, if the Froude number is less than 1, then we have subcritical flow. And if the Froude number is greater than 1, we have supercritical flow. Putting this into practice, let's say we have a rectangular channel that is 3 meters wide and carries a flow of 5.5 meters cubed per second. Find the critical depth, the critical velocity, and the critical slope if Manning's n is equal to 0.02. All right, so our critical equation is q cubed divided by g is equal to the critical area squared. I got my cubes and my squares mixed up. Squared cubed over the channel width TC. So what do we have? Our flow rate of 5.5 meters cubed per second all over gravity, 9.81 meters per second squared, is equal to my area, so that's 3 meters times my critical depth YC cubed, and Q is squared, all over the channel width of 3 meters. And solving for my critical depth, I get it to equal 0.6997 meters. So with the critical depth and a channel width of 3 meters, I can now calculate velocity. Q is equal to velocity times area. My critical velocity is going to be 5.5 meters cubed per second divided by 3 meters times 0.6997 meters, which is equal to 2.62 meters per second. Last, to get slope, we need Manning's equation. And Manning's equation for metric is the 1 over n, so that's going to be 5.5 meters cubed per second is equal to 1 over the given Manning's n of 0.02 times my area, 0.6997 meters times 3 meters, and my hydraulic radius, which is going to be my area, all over my wetted perimeter, raised to the 2/3, and all this times slope to the 1/2. So my bed slope, I calculate it to be 0.00736. This time we're given a channel with a sluice gate. So the sluice gate is there to force a different flow regime. So I have a depth of Y1, and then downstream I have a depth of 1 meter. I have a velocity downstream of 5 meters per second, and my cross section is rectangular with a depth of 1 meter and a width of 2 meters downstream of the sluice gate. I wish to find the critical depth at minimum specific energy at the current flow rate, and then I want to name the flow regime. All right. The critical depth at minimum specific energy for a rectangular cross section, we have a cheater equation, YC is equal to 2/3 E min. And that's equation 12.8 in your textbook for rectangular channels only. And remember that we have conservation of energy. So energy 2 is equal to energy minimum, which is equal to the y plus the velocity head. So plugging that in, since we have all the downstream information, that's going to be 1 meter plus 5 meters per second squared all over 2 times 9.81 meters per second squared. So we end up with an energy 2, which is equal to the minimum energy of 2.274 meters. If I multiply that by 2/3, I'm going to get 1.52 meters for the critical depth at minimum specific energy. If I want to find it at the current flow rate, let's label these. We'll call you A, B, and C. So if I want to find it at the flow rate, that's the equation that we used earlier. Q squared over G is equal to the critical area cubed over the channel width. So that's going to be 5 meters per second squared all over gravity is equal to the critical area all over the channel width. Solving for y critical, we get this to be 1.37 meters. Next is flow regime. Is it supercritical, subcritical, or at critical? We can find that with our Froude number and comparing it to 1. That's velocity divided by the square root of gravity and the hydraulic diameter. So plugging in gravity of 9.81, the velocity that was given to us at 5 meters per second, and our depth of 1 meter, we have a Froude number of 1.596. This is greater than 1, so we are at supercritical flow. Okay, we also knew that because our critical depth is 1.37 meters or 1.52 meters, depending on if we're looking at critical depth by minimum energy or critical depth by flow rate. And both of these are greater than the current depth that we are flowing at, which is 1 meter. So this also tells us we're at supercritical. Why the two different critical depths? Remember, one of them is at minimum energy, so that is at maximum flow rate. That's A, the 1.52. The other one is at the given flow rate. What is our critical depth? That's the 1.37. So we've got two different things going on here. One of them is at minimum energy with maximum flow, and then the other one, or optimum flow, and then the other one is at current flow. What's our critical depth? And then we check with our current situation, what's the Froude number, and it's over 1, so it's supercritical. What if we want to find the flow regime and the critical depth of a cross-section that is not rectangular? So I have a trapezoid here with a 1/1 side slope on both sides. It's symmetric and a depth of 1 meter, and it's flowing at a rate of 10 meters cubed per second. Okay, so find the flow regime. We need to know if it's supercritical, critical, or subcritical, and we're going to use the Froude number. Our velocity is going to be the flow rate divided by the area. So we've got a trapezoid, so that is going to be 1/2 of 3 meters plus 5 meters times a depth of 1 meter divided into the flow rate of 10 meters cubed per second. And you're probably wondering where I got that value from, because I didn't give you the width of the bottom of the channel, which is 3 meters. And if I have a rise over run of 1, that means it goes out 1 meter on either side. That's where the 5 meters comes from. So that gives us a velocity of 2.5 meters per second. And then I need my hydraulic diameter, which we talked earlier, is A over T. So that again is the 1/2 3 meter plus 5 meter, 1 meter, all over that T. T is that surface width, which is 5 meters in our case. For the rectangular channel, it was just width of the channel. But because this is non-rectangular, we have to calculate our hydraulic diameter, which in this case is 0.8 meters. Plugging that into our Froude number, I'm going to have 2.5 meters per second all over gravity and the hydraulic diameter. And we end up with a Froude number of 0.892, and that is less than 1, so we are at subcritical flow. To find our critical depth, we're going to use the equation AC cubed over T is equal to Q squared over G. So my area is going to be 1/2 3 meters plus 3 meters plus 2 times whatever my critical depth is, because I have a 1-to-1 wall length ratio, times whatever my critical depth is. That whole thing's going to be cubed all over T, and so T is going to be 3 plus 2 times whatever the critical depth is. And this is going to equal to our flow rate, which is 10 meters cubed per second, all over gravity, 9.81 meters per second squared. And I am not going to lie, I plugged this into a math solver and I get a critical depth of negative 1.931 meters and 0.934 meters. Now obviously for water flow, a negative value is not going to be any good, so our critical depth needs to be the one positive answer that we got.